Hello everyone. So this is Child's Math 4, and I just started working on this, on my iPad a little bit beforehand. So just to kind of walk you through, for this question, you are given these two intervals. You can integrate with respect to x or with respect to like the y boundaries, you could call them. Um, and it just depends on what you're isolating and subbing in for. So you could isolate for y, and then have it all with respect to x, and then go about it like that. But the easiest way to do it, because I just saw it, was like 1 to 2. So you sub in for x, and you're going to have nothing but y variables. You're still integrating with respect to dx on this side. We still have 11y squared, by the way. But you have to get this function in a way that you can sub in dx and have dy. And this is exactly what we do. So we take the derivative of both hand sides, and we determine that dx equals 2y dy. Sub that in and expand, and we get to something like this. So if we carry on, we'll have the integral from 1 to 2, 2y cubed minus 15y squared plus 14y dy. And this is evaluated as y to the 4 over 2 minus 15y. Actually, this will just simplify down to 5. 5y cubed plus 7y squared. Evaluate 2 to 1, and this ends up equaling negative 13 over 2 after you fully expand it out. So that's question 1. Question 2 is a little bit different, but it's also not so bad. So you see how they're giving you ds now. We're gonna get a formula sheet. I haven't seen him print it yet, if I'm being completely honest here. But that's fine for the most part right now. I just need to pull up when I wrote down this ds question, because I think I just okay. So for the second question, you are you're supposed to get this all with respect to dt. So they tell you y equals x to the 7, okay, and with ds, okay, when you see ds, associate that with the line integral of g at xy, this what was the name of it? I don't know. You just more than one variable function, ds, and then this will equal or be equal to your boundaries times g at f at t and g at t. This is a good way of looking at it when you separate it, times the normal of f prime at t squared plus g prime at t squared. That's about it. Okay. The normal, by the way, doesn't really do anything. You're really just subbing in the derivatives. But yeah, let's go about finishing this question. So what we're doing here essentially is we can sub in immediately y for the respective function. So we know we're integrating from 0 to 1, and we're going to have x to the 7 times x to the 4 ds. Okay. From then on, we get x to the 11 ds. And you might notice that we don't really gain anything from this approach, because we're told that to evaluate at ds, we have f at t and g at t, and right now this is just one singular function, and it's not even with respect to t. So we got to break it up. And so what we can say is, if we call x t, then y equals t to the 7. Okay? And so we eventually come down to x double prime, but now we've parameterized it. Yeah. So now the integral from 0 to 1 doesn't become x to the power 11, it becomes t to the power 11, which is now workable. So ds, okay, is equal to dx dt squared plus dy dt squared. This is very familiar. If we evaluate dx by dt, we get 1, and dy by dt, and we get 7t to the 6. Okay? Continuing on, we get 0 to 1 of t to the 11. We now sub that in, and we're going to get 1 squared plus 7t6 squared, which is 49t to the 12. Okay? Right here, we can do a u sub because we see that we have t to the 12. And so a derivative down will get t to 11, so we can cancel out that. Let's add a page. Okay. So what we can get here is u equals 49t12 plus 1. du equals 588t11 dt, and dt equals du over 588t11. Okay? And so we are going to get 1 over 588, the integral 0 to 1. The t11s will cancel out. We're just going to have square root u. Okay? And so we get 1 588 t over 3 u to the 3 over 2. Evaluated at 1 and 0. You could bring the 2 over 3 out. So you'll really get 1 over 882, and then it's just going to be 1 after you sub in like the thing, the u, which was 49t to the 12 plus 1 to the 3 over 2, evaluate at 1 and 0. This will get you 1 over 882 times 50 to the 3 over 2 minus 1, which is what we have right here. Okay, so question number 3. This question was pretty fucked up. I'm not gonna lie. I was really confused when I was doing it, if I say so myself. So let's do the best that we can to break this down. I think I have like 3 tries on this damn question because of how hard it was. Oh yeah, this was the question I was solving down today. Okay. So, let's go about doing this. So the easiest way to go about this question is to understand that, okay, well, you're asked for the work done, okay? Work equals the integral of force. That's a physics concept that we learned a while back, okay? So we know we're going to have to take the integral, and we know we're going to still kind of build off of what we learned because it's a multi, I forgot the name, but you just think of it as a multivariable integral. And yeah, you're going to have to still go along the same line integral kind of approach that we've been doing. Okay, so to do this, what we can say then is that we have the integral of c for f of like dt or like whatever variable you'd like, okay? So our c is what? Our c is our line segment, because all of these points right here are producing a line of some kind that spans from one to the other, okay? So we have 2 line segments, C1 and C2, okay? And to clarify, C1 line segment goes from -3 to 3 to 0, 0, and C2 is 0, 0 to 3 and 6, okay? Now what we can do, because it's a line segment, is create a function that represents the line. And so generally when we create our functions, we have our initial point plus our variable times the direction vector. And the direction vector in this case is the difference in the corresponding interval. Sorry, I should say the corresponding domain or range, to be more specific. So for x, it'll be the domain, which is all the values of x that can exist. And so the difference between that will be the direction that it's going in. Okay. And I think I wrote something down here, which is like, since it points in the change in direction, its difference is the direction. So I hope that clarifies that up. So for C1, let's just mark this as C1. We initially start off in x at -3, and then we go for our difference from 0 as our x2 minus -3t. And so our x vector is plus 3t. Y, in the same fashion, our initial y value is 3, and then plus y2, 0 minus 3t equals 3 minus 3t. Okay. So let's just start to try and make our first integral, our first line integral, which would be c1 f times dt equals c1 9xy dx, evaluating the first portion with respect to its vector I, along I being along the x-axis, plus 6y squared times dy, evaluating this along the y-axis, which is j. So this is our j, and this is our I. Okay, 1 second. Okay, so back to where we were. Now, if we go to try and evaluate this, you'll notice we're missing our dx and dy variables. And so that's literally just the derivative of these two. So our dx would be with respect to trying to evaluate this under one variable would be t. So we're trying to get this with respect to t. Okay. So we get just 3t, or just 3 dt. And then for dy, we're going to get -3 dt. Okay. And you're going to sub in everything that you got. So -3 plus 3t times 3 minus 3t times 3 dt plus 6 times 3 minus 3t squared times -3 dt. Okay. So you're going to expand all of that out and then evaluate it under the integral. Eventually you'll get down to a number, and for me, for C1, it was -135. Remember, you're taking this with respect to 0 to 1 for everything. Okay, and then we do something similar. Well, we do the exact same thing for C2. So C2, our x equals 3t, and our y equals 6t. Dx equals 3 and dy equals 6 dt. And our integral will look like 0 to 1 of 9, 3t times 6t times 3 plus 0 to 1, 6t squared times 6. Evaluate this all at dt, and you will get 594. And now we can just add up the, if we were looking for c at f, right, times dt, and we got c1f dt plus c2f dt, then we can also just add up their corresponding values, which was -135 plus 594. Let me toss that into a calculator. -135 plus 594 equals, oh, not that, equals 459, which which is what we got right here, which is correct. Sick. Moving on to number 4. This question was misleading. It's more so the newer, like, line independence lecture stuff. So like 9.9, I believe 9.8 was line integrals. This is line independence. So 9.9 for sure. So we're asked to just evaluate f times dr. Okay. If we want to integrate f, that's going to be fucking disgusting. So what are we looking to do? Well, okay. We can, and I'm trying to phrase this in my head too. We can calculate the gradient to see if this is conservative or non-conservative. If it's conservative, then I believe we can add up the integral of all of our separate, functions, or separate partial derivatives, to get a final function that represents something we can evaluate. So let me just show you what I'm talking about. And the conservative, non-conservative part I still need to study, but this is the most that I understand as of now. So we're calculating basically the curl to see if it's conservative or non-conservative. I don't know what they call it new, but it's literally just the curl. This is the exact same thing that we did in the last assignment. It's called the curl. Sorry. And then what we have here is all of the separate functions. I don't write them all down. I'm not going to, because it's just so much writing, but that's about it. And if this equals 0, then it's conservative. Okay. So we can evaluate, all of these. So that's really where the work is here, is evaluating this. And a really good way to think about it and kind of approach it is, the partial derivative with respect to x equals, and just sequentially count, backwards, or so just keep counting forwards. You'll see what I mean. So this is the partial derivative with respect to y minus the partial derivative with respect to z. We go to y, and now we have the partial derivative with respect to z minus the partial derivative with respect to x. Now we shift over another one, equals the partial derivative with respect to x minus the partial derivative with respect to y. And that's exactly what it is. And you'll notice, I'm not going to calculate it again, but you'll notice all of these are 0. And you have any line in the determinant, and it will equal 0. The determinant will equal 0. So yeah, so that it is a conservative function. Let me add a page. And I think it'll be like that for almost all of your guys' questions as well. Now, we need to construct f. And the way that I saw it, and I'm not going to take credit for it, but the way I saw someone online solve it was, find the partial derivative of the function at, its corresponding. Okay, so you're evaluating the function at x, right? So what function are you looking to evaluate the partial derivative with respect to x at? This one, okay? And sorry, you're not calculating the partial derivative, you're taking the integral of that. So the integral of this first one with respect to x, you'll notice that you're just going to add an x here, and this is going to go x to the 10 over 10. You're going to cancel out the 10s. That's about it. So I'm going to write them down, but just know that's what I'm doing, okay? I wrote this down neater on the next page. Okay, so x to the 10 times ln 7y squared plus 4 plus 7x 7 to the 8 y Oh my god, I'm fucking up the partial derivative sign. Or the sigma. Okay. And then you get x to the 10 times ln 7y squared plus 4 plus 5 to this zy. And then this one you get 4 cos z pi plus 7x z to the 8 plus 5yz. So these are all your functions. And what you're doing is basically just adding all of these up. But there's a really huge caveat. Holy shit, I'm having a stroke. Okay? The caveat is that you're never adding repeated terms. So that's the gist of it. So you're only going to add one of each unique term. And so you'll get, for me at least, x to the 10 ln 7y squared plus 4 plus 5zy plus 7x to the z to the 8, x times z to the 8 plus 4 cos z pi. Okay? Now, now this is your f. Okay, or your gradient. You're looking for dr now, and you're given r at t. Let me open this up in front of me, just so it's easy to access. Okay. So we're at 4, yeah. So r at t equals t cubed plus 1 I plus t squared plus 2j plus t cubed at k. Now, how do you evaluate r since it's now it's a function now? Before we could just take the derivative, but now we have to yeah, actually, why wouldn't you just take the derivative? Honestly, I don't know why you would just take the derivative. I would like, my instant idea would just be to take the derivative and then evaluate it at 0 and 1. But you don't, unless you do. No, I feel like you'd get way different. Actually, hold on. Let me try something really quick. I really doubt this is gonna work, but let me see. 3t squared plus 2t plus 3t squared. Okay, I just gotta see something really quickly. If I evaluate at 0, r at 0 equals, yeah, it's just 0, 0, 0. Yeah, okay. If you have a point that's just 0, 0, 0, yeah, you can't evaluate that. Because then also you'll get 3, 2, 3, and then it's just what the points at 3, 2, 3 are, which wouldn't get you the correct answer. Okay, I don't know why you can't just do dr, but to solve your question, because that's what we're being tested on, you just evaluate r at 0 and r at 1 respectively. So for me, when I plug that in, I got 1, 2, 0 as the coefficients. Hold on. Yeah. Yeah. Sorry, I was wondering why that wasn't making sense. T cubed plus 1i plus t squared plus 2j plus t cubed k. Yeah, so I get 1, 2, 0, and then r at 1, I get 2, 3, 1 as the coefficients. Okay? And so finally, what they're asking you to evaluate for is now equivalent to f at 2, 3, 1 minus f at 1, 2, 0. And that's this f right here. And for me, this was 2 to the 10 ln 67 minus ln 32 plus 21. Okay, so getting right back into the loop. So we have this really nice keyword here, conservative. And so we're going to calculate basically the curl of f. And we have a conservative force if the, so we break this up into two categories. We have Q and P. And we basically want the partial derivative of Q with respect to x minus the partial derivative of P with respect to y. And we want this to equal 0. Okay, so this is what, if this equals 0, then we have a conservative force. Okay? Or sorry, not conservative force, conservative function. And okay, so if I calculate the first one, and remember, we're going to be using the same formula, which is this one, all throughout. The first one, after it was calculated, was 8e to the 8x plus 6 sine 6y minus, actually, I put it right here, 8e to the 8x minus 6 sine 6y. And because we're going to have that positive 6 sine 6y, this does not equal 0. So it's not a conservative force. Secondly, we're going to have oh, sorry. I calculated. Oh yeah, I calculated. That's the second one. Okay. So then let me do this. Okay. Get rid of this. So the first one will be, after it's calculated, 64 x to the 7, y to the 7, minus 72 x to the 8, y to the 7 does not equal 0. Okay, that's great. And so finally, the last one after being calculated, it's quite long, but it ends up, after you expand everything out, 2y e to the 2xy plus 4xy squared e to the 2xy plus 2y e to the 2xy minus 4y e to the 2xy minus 4xy squared e to the 2xy. So we see that these two cancel, and then, when you add these two up, it'll also cancel with that. And so this one does equal 0, and so it's just the final one, which was D in my case. Okay, so these questions are actually quite similar to, I think it was Calc 1. Pretty sure Calc 1 we learned reversing the order of integration. I think the only thing that's different here, actually, yeah, no, nothing's different. So remember with these questions, just make sure that you're drawing out a good diagram. That's the best piece of advice that I could give. So if we go about drawing off our diagram, it doesn't have to be super in-depth, but so when we usually have a function like this, which is a square root x, we have a function that looks like that, right? And so if you go to flip it the other way around, where you have x equals root y, you're just translating it up like this, okay? And if it was negative, it'd go down, but yeah. So you have a function like that. And the reason why we're going about drawing this out is because we're looking at our boundaries, right? And so it's telling us we have dx with respect to this. So we have x equals, root y over 8. I don't really care about this part. I just care about, what's happening with the variable function. So, and then it's going from x to x equals 4, okay? So then we know that we're going from like this function up until 4, okay? And I'm going to draw some lines here. So we have this line, okay? And then we're going up, so dy, so we're going up from 0, so I'll also put a line there, okay? Up until 1,000, 1,024. So let's write those in. So this is 1,024, this is 0. Okay, perfect. So we're going, from this function up until 4. And the best way to look about doing this is if you're going to reach that function, right, your initial kind of starting point's right here. You're going to reverse the order of integration. So what I always like to do is I like to just write my initial double integral, my function x cubed plus 7, and then flip the order, so dy and then dx. Okay, so if I'm now integrating up, right, my slice kind of looks like this now. So I'm now going from 0 up until I touch this function, but I can't represent that function with respect to x anymore. I have to respect it I have to put it with respect to y. And so if I take this and I resolve, I'm going to have y equals 64x squared. So that's what we have to start with. And then we're going to keep integrating upwards until we hit the top, which is 1,024. So I'm going to go from 64x squared to, sorry, that's incorrect. Yeah, this was the previous one. You'll know when you do these questions, and I mix up myself sometimes, that you never have the same arrangement, and you shouldn't, because you're switching the order of integration. You should never have the same boundaries in the same place, unless there's like zeros. Zeros is very common for it to reoccur. So really we're going up from the baseline 0 up until the end of this function here. Okay, so there it looks like 0 to 64x squared, and so that's our y, and our x is starting off from 0 in the y-axis up until 4. So we're going to go 0 to 4. So you see how this 0 stays in the same place. And then you go about evaluating this, and the first time around, because this is, none of this is respect to y, you're going to get, 0 to 4 y x cubed plus 7, evaluate at 64x squared 0 dx. And you go about evaluating this, you're going to get 0 to 4, 64x squared x cubed plus 7. You're going to do a u sub here because you have x cubed plus 7 right here, and you have an x squared, and you want to cancel that out. And so after some work, you're going to get 128 over 9 times 4 to the 3 plus 7, 3 over 2 minus 7 to the 3 over 2. And if you do a u sub and evaluate this integral, that's what you'll get. Okay, cool. And this was the answer. Okay, cool. So now we go to 7. We're gonna do the diagram once again. Diagram is our favorite friend here. Okay. So now what we're gonna do is so let's start with dy. So we have ln x. In this case, we have ln x, and so ln x, where does it start from? It starts from 1. Can't have ln of 0, and so your equation starts from ln x, and ln is a function that kind of goes like this. Okay? And then we're going up until 2. So if this is now y equals ln x, right? And we're going up until 2, then we're going up until, I'll put it right here. This is 2. So if I run my line across, this is what I'm looking for. And I started at 1, which I could put, a vertical line through. And I'm going up until like e squared. Let's just say e squared is approximately, I think it's like 6.3, 6.28. That's just fine, e squared like that. And this is y equals ln x. Okay. And remember before we were integrating, let me bring this line up a little bit. Just for the sake of, okay. So before we were integrating initially with respect to dy by dx, we're going to go about it the same way. So we write just our function. Now it's dx by dy. So now we're integrating horizontally, okay? Now we were going up until 2, right? Now we're going to go horizontally. So if we're going horizontally, right, we're starting from the left-hand side going to the right. And so what that looks like is integrating not until this, but until the end of our function. That's a huge error that I've personally run into, but you're integrating until the end of this function. And so you have to put this with respect to x. With respect to x, you get e to the y. So your end boundary, a good way of looking at it is, y2 equals e to the y. And we're starting off at 1. So this is y1. Actually, I could just write it down like this. x1. Okay? And now to look, from bottom up, this is starting, there's no, negative value. So it's starting off at 0. And then we're going up until 2. So that you see, like that one, even that one didn't stay constant. Okay, so the first one with respect to x is going to be, x 0 to 2 over e to the y minus y. And this is going to be evaluated from e to the y over 1. What you'll get here is e to the y minus 1 over e to the y minus y. Notice if you take the derivative of the denominator, you'll get the numerator. So we could do a u sub here for e to the y minus y. Inevitably, you'll get ln of e to the x, e to the y, because this is with respect to dy at this point, minus y. Evaluate at 2 to 0, which is ln e2 minus 2 minus ln 1, which is 0. And so taking this part right here, that's what we got. Okay, thanks for tagging along. We'll see you in the next video.